Hi, this is Srimitra, Professor, Department of Mathematics, Siddharth Institute of Science and Technology, Puttur. In this video, we discuss about the topic eigenvalues and eigenvectors of a matrix. So the first one is eigenvalues. The definition: if capital A is an n-line matrix, then the equation it is determinant of A minus lambda A equal to 0, and here I is the identity matrix of the same order of capital A matrix A is called the characteristic equation. This is called the characteristic equation, and the roots of this equation is called the eigenvalues. So if the matrix is of order n by n means the characteristic equation is also the nth degree equation, polynomial equation. So we get n eigenvalues for that matrix. To compute this one, Ax it is del of A minus lambda equal to 0. By expanding this determinant, we get the characteristic equation. By solving it for lambda, we get the eigenvalues. And next one is eigenvectors. Definition: an eigenvector of a matrix capital A of n by n matrix, non-zero matrix, such that Ax minus lambda x equal to 0 for some scalar lambda. A scalar lambda is called the eigenvalue of A if there is non-trivial solution of x of such that x is called an eigenvector corresponding to lambda. Lambda is an eigenvalue of n by n matrix. Similarly, if the equation Ax minus lambda x equal to 0 has non-trivial solution. So it is the definition of eigenvectors. If any vector x satisfies this equation, A minus lambda I into x equal to 0 is called the eigenvector. X is called eigenvector corresponding to the eigenvalue lambda. Now some properties are there. For a triangular matrix capital A, the diagonal elements of matrix A are the eigenvalues for that matrix. And second one, lambda is the eigenvalue of A, the eigenvector x bar, then 1 by lambda, that is reciprocal of that eigenvalue, is the eigenvalue for the inverse of the matrix capital A and corresponding to the same eigenvector x bar. And third one, if lambda is an eigenvalue of A, then lambda is also the eigenvalue of its transpose of matrix A transpose. And sum of eigenvalues, all the eigenvalues, if you add all the eigenvalues, that is equal to the trace of A, and if you multiply those eigenvalues, that equal to determinant of A. And next one, n-one matrix A is n-one matrix, then it is invertible. Is implies to it does not have any eigenvalue of 0. Similarly, the reverse also. If any matrix does not have eigenvalue 0 means it is invertible. That means A inverse exists if and only if it does not have any eigenvalue of 0. That is, 0 is not an eigenvalue for that matrix. And for example, to calculate the eigenvalues and eigenvectors of a matrix, let us consider a matrix. This is a matrix with row elements 2, 0, 0, 0, 3, 4, 0, 4, 9. Now, to calculate the characteristic polynomial, we take the equation that of A minus lambda I equal to 0. First, to calculate this expression, that is a polynomial of third degree, because the matrix A is 3 by 3 matrix. So we get third degree polynomial. To expand this one, we can get, this is the characteristic polynomial. It is called the characteristic polynomial minus lambda cube plus 14 lambda square minus 35 lambda plus 22. By solving this equation equal to 0, we get the roots of this polynomial is 2, 1, and 11. So these are called, these three values are called eigenvalues for the matrix capital A, which are the only three eigenvalues of the matrix A. So corresponding these eigenvalues by calculating with the equation Ax minus lambda A equal to 0, A minus lambda A into x equal to 0. That is the equation to calculate the eigenvectors. We get three vectors 1, 0, 0 transpose. This is row matrix transpose, means a vector can be denoted with a column matrix, that is one column, 3 rows. That is, since it is a 3 by 3 matrix, it has 3 rows and one column. So 1, 0, 0. This is corresponding to eigenvalue 2, and corresponding to second eigenvalue 1, the vector is 0, minus 2, 1, and for the third eigenvalue corresponding to that value is the vector 0, 1, 2 whole transpose. These are the three eigenvectors. Next one is, by using these eigenvalues and eigenvectors, we can diagonalize a matrix. Means we can convert a matrix into a diagonal matrix by simply multiply this product P inverse AP equal to T. If you multiply A with P and P inverse, here P inverse or P is called the model matrix, means it is the matrix obtained by three eigenvectors as a column. P is a column. First column is the first eigenvector. Second column is the second eigenvector, and third column is the third eigenvector. And if you calculate the P inverse of the matrix, then we get P inverse. If you multiply P inverse AP, then we get the diagonal matrix corresponding to the given matrix capital A. So, for example, if you take this matrix 0, 1, minus 2, 0, 1, 0, 1, minus 1, 3. By calculating the characteristic polynomial and the roots, we get it is the characteristic polynomial theta of A minus lambda equal to 0. We get three eigenvalues 1, 1, and 2. These are the eigenvalues for this matrix. And to calculate the characteristic value vector, eigenvector, these are the three vectors. V1 is 1, 1, 0. V2, it is corresponding to the eigenvalue 1 and is also corresponding to eigenvalue 1, 0 to 1. And the third one is 1, 0, minus 1 is corresponding to eigenvalue 2. By considering these three vectors as three columns of a matrix, that matrix is denoted with P, it is called the model matrix. It is P is a model matrix. So P is also a 3 by 3 matrix. So we can calculate the P inverse of a matrix by using previous knowledge. We can calculate P inverse. So P inverse into A into P. It is P inverse into A into P. We get this matrix. It is a diagonal matrix, except the diagonal elements. All the remaining elements are 0. And if we observe clearly, the diagonal elements is all again the eigenvalues of the given matrix. 1, 1, 2. These are the first two eigenvalues, and it is the third eigenvalue. It is the diagonal matrix D. It is a process to find a diagonal matrix by using eigenvalues and eigenvectors. And another example is here. Let us take this matrix A with same order 3 by 3 with the elements 8, minus 6, 2, minus 6, 7, minus 4, 2, minus 4, 3. It is a characteristic equation. Let B lambda q minus s1 lambda square plus s2 lambda minus s3 equal to 0. It is a third degree polynomial because the given matrix is 3 by 3 matrix. By previous knowledge, you can calculate s1 and s2 sum of the roots, product of the roots, sum of the roots taken together, 2 at a time. These values become. So the lambda values are here 0, 15, and 3. 0, 3, 15. These are the three eigenvalues for the matrix A. Now each one, that is A minus lambda into x equal to 0 is the eigenvector. To find the eigenvector, that is the equation. By substituting each and every eigenvalue in this equation, we get the three eigenvectors. First of all, we substitute the eigenvalue 0 here. So if you substitute lambda equal to 0 in this equation, we get this is the equation. By simplifying this equation, we get three values of x, 1, 2, 2. x1 is 1, x2 is 2, and x3 is 3. Sorry, 2. So it is the eigenvector corresponding to the first eigenvalue 0. So it is the first eigenvector. 1, 2, 3 is the column matrix. And next one, second eigenvalue, we substitute in the same equation. The second eigenvalue 3, it becomes the equation 5 minus 6 2 minus 4 minus 4 2 minus 4 0 into x1 x2 x3 vector equal to 0 0 0. So it is a homogeneous equation, matrix equation. So by calculating the system of equation by using system of equations, we get the value of x1 x2 x3 as 2 minus 1, sorry 2 1 minus 2. By simplifying in this way, This is the procedure to find x1, x2, x3 here. So we get x1 is 2, x2 is 1, x3 is minus 2. So the second eigenvector is capital x2 is 2, 1, minus 2. Similarly, for the third eigenvalue, the corresponding eigenvector will become in this equation minus 7, 6, minus 6, 2, minus 6, minus 8, minus 4, 2, minus 4, minus 12 into the vector x1, x2, x3 equal to the null matrix 0, 0, 0. Again, by simplifying the system of equations homomorphic system, we can get the vector as 2, minus 2, and 1. So it is the third eigenvector. Right? For x3, the third vector x3 is 2, minus 2, 1. So we get 3 eigenvalues and 3 corresponding eigenvectors. Now the normalization, after normalization, we get the model matrix capital P is this one, 1, 2, 2, 2, 1, minus 2, 2, minus 2, 1. So it is the model matrix P. Now P inverse AP. Since here we can observe that it is these 3 vectors are orthogonal. That means x1 transpose x2 equal to 0, x2 transpose x3 equal to 0, x3 transpose x1 is also 0. It is called the orthogonal vectors. So each and every vector is orthogonal. Then we can say that its inverse is equal to its transpose. So matrix P is the model matrix. It is model matrix. Its inverse is equal to its transpose. So if you calculate the P inverse, you can calculate here its transpose. In this problem, the model matrix P is denoted with capital N. Is also the same. It is normalized matrix. This means capital N means here the normalized matrix, and in general we can denote it with capital P is the model matrix. So here in the place of P, we are using the notation as N, normalized vector N. So if to calculate N with N inverse, simply it is enough to calculate its transpose. So N transpose, it is N transpose. And by the diagonalization procedure, we can multiply N transpose A N simply. We can get the diagonal matrix. This is the diagonal matrix N transpose A N. It is a multiplication process of three matrices. We can get 0, 0, 0, 0, 3, 0, and 0, 0, 15. So it is also a diagonal matrix, except the diagonal elements, all the elements are zeros. And the diagonal elements, observe here the diagonal elements are the eigenvalues. First eigenvalue is 0, second eigenvalue is 3, and third eigenvalue is 15. So we can convert the matrix capital A as a diagonal matrix by this procedure. So it is the diagonalization of a matrix by using eigenvalues and eigenvectors. This is the concept of eigenvalues and eigenvectors, and that the diagonalization of a matrix. These are some references and web resources references. Thank you very much.